We use chemical equations to represent chemical reactions, because if we describe them in words, it'd be an awful lot of words. And words can sometimes be hard to look at. It's hard to just immediately take in what it's meaning. So a chemical equation is not exactly a picture, but it's more visual than just reading a bunch of words. And we have, of course, conventions for how we write our chemical equations. So the substances that are on the left side of the arrow are called reactants. The substances on the right side are called products. The arrow is that these chemical equations are a little bit like math equations in some ways. The arrow is more like an equal sign, and so this is going to equal that, but it indicates a direction. We're starting with this, we're going to that. Usually we have the arrow going to the right because we read left to right. But these are the reactants over here, and these are the products. So the reactants react to produce the products. So you've got things reacting, and they're producing the products. What we have here after the formulas for each of these compounds and elements, in parentheses, is a symbol to describe what is the physical state of that compound. We don't always have to have these, but when they are there, that's what they mean. So G means that this compound is a gas, and this is a gas, and a gas, and a gas. It's all gases. These are the 4 different symbols that we use. G for gas, L for liquid, S for solid. That makes a lot of sense. Then we have AQ. AQ stands for aqueous, and aqueous means dissolved in water. It's similar to the word agua in Spanish that means water. So aqueous means it's dissolved in water. Let's look at this chemical equation. So here are the chemical formulas, and up here are models of those chemicals. So CH4, the carbon is the black ball, and there's 4 white balls on it. Here's the oxygen. Oxygen is often represented as a red ball. Here we have, come on, pointer, come on, there we go, carbon dioxide and water. Now, if you just think of these in terms of building blocks, could I take this one apart and this one apart and make these 2 things without any leftover pieces? No. No, I couldn't, because there's only 2 red balls over here, and over on this side there's 3. And sometimes, if you have any experience playing with Legos, sometimes you want to be able to take a white block and make it into a red block, but you can't. Atoms don't change in a chemical reaction. They just get rearranged. So this description is not very good, because this can't happen. You can't have one of these and one of those reacting to make one of these and one of those. We have to observe the law of conservation of mass. Matter has to be conserved. We can't have atoms disappearing and reappearing. So we have to adjust our equation. The other problem with this equation has to do with the hydrogen atoms, the little white balls. Here we had 4 white balls, and now we only have 2. Where'd the other 2 go? Well, they didn't disappear. Our description of the reaction isn't quite right. So we need to create a balanced chemical equation. CH4 is describing this molecule. O2 is correctly describing this molecule. But how we've put them together isn't working. So to balance the equation, we put coefficients into the equation. The coefficient is a large number in front of the symbol, the chemical formula. So what this means is 2 of those. And here in the picture now we see 2 oxygen molecules. Sometimes it's very tempting to change the subscripts. You can't do that. That changes what the chemical is, and then you're talking about something else. So if we have 1 of these and 2 of those, Now we can rearrange those and make one carbon dioxide, and we can make 2 water molecules. And all of the balls that we started with show up in our products. And then we know that we have a balanced chemical equation that's accurately describing the actual chemical reaction that's taking place. Any questions?